probably most of you know Edward. Those of you who don't know, just, I don't know, go on Haskell IRC channel. Haskell Cafe, or just search for his name. He's everywhere. If you happen to come to Boston, he has a user group there.
Yeah, Boston Haskell meets third Wednesday of every month. So if you happen to be in the Boston area, feel free to drop by.
And apparently he's coming to the Bay Area every once in a while, so we might get lucky and get more of his talks. And he seems to be working on new and cool stuff every time, so so we get more and more
I get
stuff.
bored easily. Is really what happens.
So yeah, so please go ahead with the topic of.
So I love Haskell. It's very good at a lot of things. There's just a few things that the Haskell ecosystem is really lacking that I find when I go to other languages. Like if I run around in the C++ community, there's a whole bunch of stuff for working with cache-oblivious data structures and succinct data structures and stuff that have been built up like over the last 4 or 5 years. And there's really just no equivalent in the Haskell community. So I want to talk a little bit about what they are, or what at least the cache-oblivious side of things, what it means, and kind of why it's not here. Just sort of like go through a little bit of like my experience with trying to actually build a cache-oblivious data structure in Haskell, and I'll actually pull up the API that resulted at the end, and we'll see how it goes. So this means that I have to talk a lot of very annoying computer sciencey stuff, just to kind of set the tone, just to say what the problem is. Which means we're going to be talking about machine models and different models of computation, and then we'll see how they map onto map and existing container types that we have in Haskell, and see how they kind of fit into this thing that I wanted to build. But really what I needed a version of like data.map that had support for very efficient large range queries. I wanted to be able to say, give me everything between this key and that key in the map. And I needed it to be faster than following all these pointers. So I wanted to be able to smash things together contiguously in memory. So I wanted to unbox data. And I'm willing to let query performance for points suffer. But I really needed to support efficient writes. And so inserts need to be really fast. I'd be happier if they were 8 times faster than they are for data.map, or something like that. That's of course assuming the result. But that was actually kind of where I was going when I came into this. I was like, I know there's this thing called the cache-oblivious lookahead array, and I wanted to see if I could build it in Haskell, and if I could actually turn it into a data structure that I could actually use. The results are a bit mixed. We'll see as we go. And so when we start talking about computation, like we've all like seen Turing machines. It's like you can start talking about that as one way to move tape back and forth or whatever, and say, well, if it's polynomial in a Turing machine, it's polynomial in any machine. But in practice, we don't sit there and derive all of our asymptotics in terms of how something would run in a Turing machine. We have random access machine models, which are basically, or pointer models and various other machine models that we have that we use for more formal analysis. Okay. And then we keep going, we can find these new, like this external memory model and the cache-oblivious model. And I'll go through and describe those in a little bit more detail. So the RAM model is, shouldn't have animated the way through. Almost everything that we do in Haskell kind of lives in the random access machine model, or the word model, depending on how you want to play with it. And it's pretty good for talking about ADTs, basically. You've got a pointer to some structure, and it's got some pointers to some other structures, and maybe you have an array here or there, and you talk about random access within the array. But when you are dealing with kind of the real world kind of hierarchies that we have inside of our computers. Since the 1980s, we don't just have one gigantic flat memory that's perfectly homogeneous to access, right? We have all sorts of caches involved inside of our computers, and it's really a lie to try and do your asymptotic analysis of your programs ignoring those hierarchies. Okay, so data.map, for instance, is a data structure that's really good on a pointer model or a random access machine model. As a matter of fact, it's as good as you can really get on that model. And so data.map is built off of what's called a binary search tree of bounded balance. A lot of folks probably are more familiar with like red-black trees or various other ways to get perfectly balanced or balanced enough trees. Data.map allows a lot more slop so that it does fewer rewrites. And that means that it thrashes the garbage collector a little bit less than a lot of the trees that people are more familiar with. It has ridiculously good constants. It's actually really hard to beat data.map, even though, by working in a better model, we should be able to pack more stuff together in memory and beat it. Just because it's so darn fast at what it does, and it fits Haskell's execution model so well. Don Lyon did the original version of data.map like 13 or 14 years ago, and then Johan Tibble and Milan Straka have been fiddling with it and improving it ever since. So it's kind of it's had a lot of very smart people making it fast. And so rebalancing inside of data.map doesn't exactly follow like the rebalances that you would expect in like a red-black tree or another self-balancing tree.
And that's because they made it so that it's faster that way.
What it does is instead it basically keeps track of like how far out of balance is the size of each of these sides, and then if it gets outside of a certain constant multiple, it just goes through and rebalances the whole thing and pulls it back up that way. That was what the Trees of Bounded Balance paper. And there's two papers. They're actually both linked from the data.map Hammocks. They're actually both pretty good reading. Data.map is actually a refinement of the techniques in those papers. There's a bunch of stuff that's in data.map that's not published. It uses different constants for all of its tuning based on all sorts of really old benchmarks and stuff. But it performs very, very well in the pointer model. And it's more about the fact that as you walk back up the tree, you're creating garbage. And so you want to reduce the pressure on the garbage collector a little bit more than you'd get if you just did a pure red-black tree. So the external memory model is like the first of these slightly better machine models that I want to consider. Slightly better being slightly more realistic in some sense. And that is, what we want to do is we want to really talk about the fact that we have CPU and memory, and then we have something slower. Maybe this is really CPU and registers, and we have main memory. Or let's just talk about one computing engine that has a cache and something that we want to go get from. So when we talk about this, we can talk about it with a couple parameters. We can say, when we go to read and write from disk, we're actually going to go get a contiguous range of data. When you go to read, a byte in a sector, you get the whole sector. And we'll say that our working memory has some size m. And for historical reasons, we'll just say that we can hold m divided by b blocks worth of memory inside of our working memory. And so we can go out and touch the disk. And what we're interested in really is, because accessing the disk is so much slower than almost anything else you reasonably want to do, that's not cryptographic on the CPU, let's just pretend everything else is free. Okay, getting the cache line is the thing that's going to kill you. Assuming you're not going off and doing crazy. You can always go through and model the contents of this thing over here using the RAM model, but it's usually just treated as free. So in the external memory model, sort of an optimal data storage format is already pretty well studied. B-trees were, Rudolf Baer came up with these things forever ago. They are provably asymptotically optimal for all sorts of different operations. For sake of discussion, I'm treating B, B plus, B star, all these different variants of a B tree as B tree. Okay, I'm not bothering to make niggling distinctions between B tree flavors. How many people here are familiar with B trees? About half. Okay, a little bit better than that. So B tree is just going to say, well, what we're going to try and do is we're going to say, let's make the fan out so that we can store multiple, instead of being a binary tree, we're going to just be like a K-way tree so that we can fit our K-way fan out into a page. Like we have multiple keys that we want to split on and all of the actual pointers to go down to the next level of the tree. A 2-3 tree is a B tree. B trees have the invariant that all the leaves are at the same height. And they have a number of interesting asymptotics that are not usually written this way, but they occupy n divided by b blocks worth of space, the update in time log n divided by b. You can search them in log n divided by b plus a divided by b, where a is the size of the result set that you're looking for. So if you're looking for a contiguous range of records in here, this will actually start seriously beating something like data.map for external reference or for external memory. Now, B trees are great for disk, as long as in general you can go through and hold the entire index in memory, and then you can go through and say, well, it cost me one disk access or something to go get the leaf level data. For one cache, a B tree is awesome, which means it was great in the 80s. But as time's gone on, we've gotten to the point where we don't have one cache. We have our CPU, which has some registers, and then that can talk to L1, and L1 can talk to L2, and L2 can talk to L3, and we've got main memory, and we've got disk, and you've got network, and you've got all these other, now it's off the local network, and that's out on the cloud. It gets crazier and crazier as time goes on. And if we look at these things, we have a huge number of constants to tune now. We've got block sizes for each one of these caches. We've got individual caches now hold different amounts of data. Right, so we have a huge number of constants to tune for. And it turns out that optimizing for any one of these caches actually means that you have to sub-optimize for others. If you want to tune for one cache, then tuning for the next cache, you wind up only being able to get within 1.2 times optimal performance. So you can actually go through and improve very nice properties of it. So when you add another one, maybe you can get to 1.3. And you get a little bit further, you get to 1.4. It actually converges to 1.444. In the limit as you add more and more caches. Okay. But if we look at our caches, in general, they grow exponentially in size, but they also decay in performance exponentially. Like it gets slower and slower exponentially to access things further. I don't think anything that I'm saying here is controversial in the least, right? We've all dealt with this stuff. So that's what sort of the embellished version of the external memory model becomes. And so tuning for all those individual parameters starts to become really onerous really fast. We can maybe do two levels, like an average human programmer can do a couple of levels of a cache hierarchy and say, well, I'll fit this thing in L1, and I'll optimize my things so they fit in 4K so I can fit my page cache or whatever. And that's about the level of optimization that the average programmer is willing to throw at this. So there's this thing called the cache oblivious model. And the cache oblivious model is actually very simple. It goes back to sort of the external memory model. And all we're going to do is we're going to say, we have one cache. But I'm not going to tell you what the parameters are for that cache. So you have M and B that you have to optimize for. But you're not allowed to know what they are. Okay? And if you can provide something where you don't know M and B, but you are optimal, you're making optimal utilization of that cache, then it turns out that by optimizing for any one cache that you don't know all the parameters for, you're able to optimize for all caches at the same time. Okay? And you will hit asymptotically optimal asymptotics. Okay? And you can model things like this is normally done for assuming since I don't get to know the parameters of the cache, before when I was talking about the external memory model, I had to consciously evict the pages of the cache. Like I had complete control over my replacement policy. Anything I wanted to do to read or write a page, I had full control over it. I've lost that when I started talking about a cache oblivious model, because I don't know how many pages I have. So we have to assume that it's going to be magically managed, right? It will be managed by, say, LRU or by a perfect cache replacement policy. And it turns out that you can actually model the loss of functionality when you actually go to decay from a perfect cache replacement policy down to LRU, because we really use LRU caches, or we use like 4-way set associative caches for our CPUs, for our L1 and L2 caches, etc. And so you can relax these assumptions by just saying, well, really you just had lower M than you thought you did. So a LRU optimized cache might be, might get 0.6 of the utility of a perfect cache replacement schedule. Or, one that's being managed by 4-way set associative maybe gets 80% of that. But you could just treat it as you have a smaller M than you thought you did. But you don't get to know what M is anyways, so it doesn't matter. Now there's some refinements to this model. You might, there's ways that B might have to be much, much smaller than M and certain other properties. But in general, as our caches get taller, as we get more and more layers of caching, it becomes harder to optimize for all of them at the same time. We just don't do it now on real architectures. So perhaps it's starting to be time to stop lying to ourselves and saying that we can optimize for them. Because really when you move data from, you move an algorithm from running on Intel to ARM, all of those things are gone. Like all the parameters are different anyway. So you have to go through and hand tune a million parameters. This is why Oracle DBAs make so much money, because they know how to tune all these magic parameters, right? Just for this particular brand of hardware. Nope, there's no Oracle DBAs in the audience. But I don't want to have to hire these people. Because I don't think that that's a skill that people should have to have. I would much rather have an algorithm that just does the right thing when it's moved onto exotic hardware. Because new hardware designs are going to be thrown at me all the time. Okay? And so for me, if I can have an algorithm that performs asymptotically optimally, but not only asymptotically optimally, but with pretty darn good constants in practice, as long as my CPUs keep getting a little bit faster, at the same rate as my towers of caches keep getting a little bit deeper, then I'm much happier with that algorithm. Okay, so that's kind of the motivation for considering the cache oblivious model. If I can design algorithms that fit into this model, then I can future-proof my code. I don't want to write code that in 2 years is going to be completely obsolete, and I'm going to view myself as having wasted time with having written that code. And if I optimize for any one architecture, any one CPU, I feel that that's what I'm going to feel. I'm going to regret having written that code in the future, because it's going to be written for assumptions that just don't hold. But the nice thing about the cache oblivious model is if I can write code for it, it's becoming more true every year. Right? In 2006, I used to look at cache oblivious code and say, that's a bad idea. The constants are so bad. But A, the cache oblivious guys have gotten smarter. They've built better tools in the meantime. But B, our caches have just gotten deeper. And so to me, it's starting to become more and more an imperative that I think in these terms, and less an option. So that's sort of the spiel. So in terms of my goal, what I want to figure out, can I provide an API that Haskell programmers want to use? Because nobody's doing cache oblivious stuff in Haskell, so why? Let's see if we can explore a little bit of that. And then I want to see if I can beat data.map, damn it. People have been using this thing for, forever. Code that was written for assumptions that held 13 years ago shouldn't be able to beat something that I write from scratch today. And finally, I want to see if I can get B-tree performance without tuning parameters. Now, I probably can't get all three of these things at the same time. Let's go through and explore, what the trade-offs are between these things. But that's kind of what I want to do. If I could have something that met the performance of a B-tree, but worked with B-tree-like performance independent of the cache layer, so that it worked for your L1 cache, your L2 cache, your L3 cache, and your disk cache. then that would be a much nicer tool. Okay. So this thing exists. Bender and a bunch of other guys over at MIT went off and built this thing called a cache oblivious look-ahead array, or a cache oblivious streaming B tree. You can download the paper. It's actually a pretty readable paper for the cache oblivious space. The cache oblivious algorithms in general tend to use all sorts of weird things. I'm not going to talk about them in a general capacity today, but you wind up seeing things like square root of n's popping up in your master theorems. Things that you just don't see. And it's because you're trying to make sure that at any cache size, which I don't get to know, I'm like within a factor of 2 of optimal for it, for some layer in this hierarchy. And so you get very weird fan-outs. Acola, on the other hand, has none of those properties, which is what makes it actually very, very nice to think about. So a cache oblivious look-ahead array, just talking about it from what it does, rather than how it does it first, matches the asymptotic worst case performance of a B tree. So it actually hits the worst case performance, not just amortized. It has very, very fast inserts. And it's designed to scale up very well. They actually started a company named Toku that sells a database called TokuTech, or TokuDB. Maybe TokuTech, I can't remember the English one. Which one's the company and which one's the database and which one's the
company, TokuDB.
All right, that's what it is. Yeah, so it's a little MySQL replacement engine that goes through and uses, it used to use Acola in the back end, and then after like their first year of business, they figured out a better thing.
They have what they call
fractal trees, yeah. Fractal trees, where if you go read the original papers on fractal trees, they're based on their Cola research. And if you read the more recent papers on fractal trees, or the recent stuff they've been talking about on fractal trees, or the patents, it's a very different beast.
They also have a MongoDB storage engine too.
Yes. So that's who Bender is. He was a guy who did a whole bunch of cache oblivious algorithm stuff at MIT, and then they started Toku, or TokuTech, and have been kind of playing around with this in the middling to big data space. The benefit that even the Cola had compared to a B tree is that a B tree performs really, really well as long as you can fit the entire B tree, like the body of the B tree, not the leaves, in main memory. But the moment you started to exceed main memory, what would happen is your performance just drops off a cliff, like at what you just go like, just a little bit too big, and then your MySQL database will never finish writing its logs or doing all the things that it has to do internally. Any of us who've had to deal with a database that's just a little bit too big for MySQL or Postgres or one of these has felt this pain. So the nice thing about the cache oblivious look-ahead array and the other fractal tree stuff that they do is that it just doesn't fall off that cliff. It has a pretty smooth performance degradation once you start exceeding the system parameters. And cache oblivious algorithms in general have this property, in my experience. And I'm rather fond of things that just don't run into a performance cliff and die. They may not make perfect utilization of the resources, but having that smooth taper when you start to exceed the resources is a very desirable thing. The problems that the Cola stuff has is that, from my standpoint, it's not a purely functional data structure. So I can't really make a nice Haskell API on it. So I want to kind of take apart what a cache oblivious look-ahead array is and see how much of it we can salvage in Haskell as a data structure that we can actually work with, like data. Okay, so I'm going to talk a bit about like a very simplified form of a cache oblivious look-ahead array first. Okay, and the idea is what we're going to do is we're going to have a linked list of arrays where each array is sorted internally. So it's like an A list, basically. It just smashed together key value pairs sorted by keys. Each array is just a sorted array of key value pairs. Nothing earth shaking. The only novel structure of the cache oblivious look-ahead array is that what we're going to do is we're going to make sure that we have a linked list of these arrays, and the later arrays in the list are much bigger than the arrays earlier in the list. Okay? And so we'll just say that each array inside of my list for right now has to be something like a power of 2 in size. Okay, and then they're going to be strictly monotone increasing in size. And the bigger vectors come later. This is a bit of a simplification. This is actually a gross simplification of the actual COLA, but it's accurate enough for reasoning about it. So if we had something like this, where we have, anyone see the little, like the dotted? So they're a little faint. Sorry about that. So if we had something like this, which would be a COLA that has 5 elements in it. We have a file that has, or an array that has 1 entry, named 5, and another array that has 4 entries, 2, 20, 30, and 40. And if I went to go and insert something like 7 into this, what I would do is I'd make a new array of size 1, and then merge it with the other array that I have of size 1. So I'll do the merge pass of a merge sort, and make it a file of size 2. Now, if I had already had a file of size 2, or an array of size 2, what I would have to do is I would have to merge that with the array of size 2, making an array of size 4, but then I already have an array of size 4, so I'd have to make an array of size 8, right? So I think I actually do that. So if I insert 8 after that, I would get another singleton file. But if I did another insert, if I went to insert 10, this would carry into this, which would carry into this, and I'd have to rewrite the whole thing. Okay, so the worst case performance of this model, the simplified COLA, is ON, right? Like our ON divided by B, because these are all contiguous storage and memory. Okay. But the amortized insert case is O log n divided by B, which is what we had for the B tree. So on an amortized basis, inserts are already as good as a B tree, just with this very simple, stupid scheme. My worst case performance is all over the place. But on an amortized basis, assuming that I only ever update the latest version of the structure, and that's the problem. So if we start playing games with, what does it mean to amortize an algorithm, we go back to just like, go back to undergrad, and then take our algorithms course, and we say, what does it mean to amortize a data structure? We start saying, well, I have a sequence of operations that I want to perform, and what I want to know is that at any given point in time, if I were to stop this sequence, does the sum of the actual costs, is that actually less than what I said my amortized cost should be? Right? So I can get away with doing some operations a little bit cheaper earlier on maybe, and then later on do a big expensive operation because I've earned credit. Right? That would be algorithms 101, how you do amortized analysis. And there's lots of algorithms actually out there that have amortized bounds that are provably better than any achievable worst case bound for the algorithm, like union find, or something I'll show a little bit later. Now there's a couple of ways that you could do this. If you wanted to prove that little equation holds, what you can do is you can assign a price to each operation, and then kind of track the costs in how your structure is laid out. And then if you make sure that no portion of the structure is out of whack in its debt, then you can say that the actual cost is less than the amortized cost. That would be the banker's method, as I think Okazaki calls it. And then there's another one, which is the physicist method, and instead of letting our credits and debits around our structure govern how we amortize things, we start from savings and then derive the cost. So we say for any given structure, it has a certain amount of potential of unused, like, extra energy. And then we pay what our actual cost is plus the change in the potential energy of our system. That's why it's the physicist method. And so you can start talking about like the new potential energy minus the old potential energy plus the actual cost. You flip this equation around, you can say that the actual cost is the amortized cost plus the old potential energy minus the new energy. And then we successfully amortize with whatever bounds that we wanted, as long as the potential at our first time step is 0, and we never dip into negative potential. So Bender and those guys went through, and in the original paper, they were able to de-amortize the algorithm that they use. Ephemerally, which means that they assumed that you're only ever going to update the latest version of the cacheability look-ahead array, because for the most part, the database guys are concerned with you have one structure and you're moving forward in time. You're making inserts and deletes. So it's a reasonable assumption in that kind of an environment. The problem is that the way that they did it was by running two threads. They have one thread that is doing inserts. That's making new blocks, new files of size 1, basically. And then it's using another thread that goes through and is making sure that it does merges on those files in such a way that it does at least log n merges for every file that we're willing to create. Okay, because if you look at it, each thing is going to proceed from life as a 1 file into life as a 2 file, and as part of a 2 file, as part of a 4 file, as part of an 8 file. It's going to keep growing, it's going to keep merging into larger and larger files. But there's at most log n files. And so it goes through at most kind of log n stages in its life cycle. So if we pay down all those log n stages before we get there, we can ensure that we never have more than log n files outstanding, or O log n files outstanding. And then each array is immutable, so what we can have is we can have this thing merging these files, and then until they merge, then you just look at the old stuff. But this is not a purely functional data structure. This is two threads that are racing, and one of them has to block whenever it gets more than log n times the number of steps the other one's taken, and all sorts of crazy stuff's going on. This isn't a structure that I want to expose to an end user in Haskell. And the way that they do that is they use redundant binary. So instead of using the binary number system that we were using before, where we either had or didn't have a file of each size and power of 2, they're willing to allow you to have, say, 2 files of a given size, as long as there's a gap that the merges can happen into in the middle. The exact workings of this aren't important. But the fact that they use a redundant binary system and that they can get away with it because they can race these 2 threads in a non-purely functional way. It's the fact that this does not lend itself to a purely functional algorithm that matters, not the exact details of this number system. And so you can prove that any addition can be done by touching above 3 digits, and so you don't have to worry about arbitrarily long carries, and you get some other nice properties. The problem with this analysis is it's flawed in a persistent setting. Nothing keeps me from taking a map and inserting a key into it, and then going back to the old map, because it's a purely functional data structure, and inserting another key into that old map. And then just working with, like just saying, oh, well, I didn't really want that version of the map. I wanted the old thing, and I wanted to keep going with it. And we do this. We work with old versions of data structures all the time. That's one of the things that we're paying for in a purely functional language, is we pay, in a strict language, we are provably paying a logarithmic factor in some algorithms. In a lazy language, we don't know if we're paying a logarithmic factor in some algorithms. But in a strict language, we're paying that logarithmic factor for persistence. And persistence happens, people use it. But persistence means that I can't execute on any operation cheaper now and pay for it later. Because what might happen is, this guy might say, well, I did 1,000 cheap inserts, so now I can afford to rebuild my entire map as my next step. But if I go back, if I time travel back right before I did that, I'm going to rebuild my entire map, and then did another insert, I'm going to go, oh, well, I did 1,000 cheap inserts, so it's time for me to rebuild my entire map. And so any one insert could cause me to rebuild the whole map, and I might have to pay for it if I just keep going back to that same version of the map over and over again. Okay? So in a persistent setting, it's dangerous to go through and say, well, we'll pay it down by doing things cheaper earlier on, and then later on we'll earn back this amortization. How many people here are familiar with this stuff? So I don't know. So I know. Okay, so a handful scattered around, so I'm not boring everyone. Okay. So this is really Okasaki's big insight, which is that laziness can often be used to resolve this issue with multiple futures by very carefully saying, when I go to do something cheaply, what I'm really going to do is I'm going to set up a thunk that has the expensive operation that I'm going to do later inside of it. And then if one of those future paths forces it, then the other future path gets it for free. Okay? And the trick is that there's not every algorithm that we don't know how to do this for every algorithm. And a lot of us strongly hypothesize that there are algorithms for which you can't do it this way. Like union find doesn't seem to be amenable to this. The known algorithms that we have for it just don't let us conquer it this way. But this does give us a path by which we can have multiple future versions of the structure. We can work with finger trees, derive a lot of their performance off of this kind of trick. And it's one of the reasons why it's often the right decision to make the spine of a data structure lazy, not math. But because you can then use Okasaki's trick to say that we can actually get worst case performance bounds that match up with what we expect, and we can actually do amortization that works in a persistent setting. It's harder. There's fewer people who can or are willing to do this. But it's actually the right way to think about things in a persistent setting. So unfortunately, this doesn't work for me. I haven't been able to make it work for the COLA. So I have to do the thing that sucks. But it's the right way. Right? This is the way that we want to think about algorithms in a persistent setting. But what's going to happen is, because I need to pack things together in memory, the values that I'm going to be packing together in the future really are dependent. I can't set up the calculation in advance in any way that I know how to do. If somebody wants to figure out how, I would give them props. Lots of props. Anyways, so if we don't like the problem, change the problem. We can give up on the worst case asymptotics, we can give up on persistent amortization, we can give up on some other things, I'm going to do all three. All right, so in all the code that I have that follows, instead of actually using redundant binary, I'm going to use another number system. And this one's actually hard enough that I should explain. So redundant binary is like all your positions are still worth what you expect a binary number to be worth. You just get you get to use a 2. Or you get to use a bunch of 2s, actually. As long as you specify, you meet some rules about where they go. With skew binary, we're going to constrain the problem down enough that the representation of each number is unique again. But we're still going to let you use a 2. Okay? So why do we want to count with binary with a 2? The reason is it lets us say something very strongly about carrying. If I increase a number by 1 under this number system, it'll turn out that I only ever have to carry 1 place. Okay, and then when we actually map this number system onto a new data structure, that has some very nice properties. So normally you're used to saying 1, 2, 4, 8, or whatever is the value of our places. But we want all of our numbers to be uniquely representable, and we want to be able to use it too. And the restriction I'm going to put on where 2 can go is 2 can be in the least significant place that's not a 0. So we can count 0, 1. Well, I need to represent 2, and I can't get with 2 by putting a 3 in it, so I have to use 2 1s. So that's how I get my 2. To represent 3, well, I have 3 as the value of one of my places, so I use 1, 3, and 0 1s. That's 3. 4 is 1, 3, and 1, 1. 5 is 1, 3, and 2 1s. And then to get 6, well, I can't get there with 7, and 1s won't add enough to 3, so I have to use 2 3s. Right? If you just work through the rules that, what we said where goes where, you only get one possible representation for every given number that we're representing. Okay? But if we look at this in terms of carrying, when I go to carry from 2, and this goes to become a 3, and then has to cap off and become a 1 and carry one place over here. This can only ever carry one place because this guy can't be a 2 because this one was. We only ever have 1, 2, and it's always in our least significant place. So that invariant is strong enough to say, well, one carry can't force the next carry for incrementing by 1. It's an interesting trick. I have another talk that I use to improve the known asymptotics of lowest common ancestor search. Actually, that one's one. But this is a very useful data structure. It's another thing that Okazaki beats to death. If you haven't read it, I highly recommend picking up Chris Okazaki's Purely Functional Data Structures. It talks about a lot of these tricks that I'm using here. And I would be a much poorer computer scientist for not having read it. So if we look at this representation is unique. If we look at this as the sizes of the files that I want to use, of the different arrays of data, I want to say I want to allow you to have an array of size 1, one of size 3, one of size 7, one of size 15. But you can have 2 of them of the same size, as long as that's the smallest size of data. So you have a sequence of arrays that are still growing in size. We're just going to map this onto the same structure that we had before. But now they've got these funny 2 to the k plus 1 minus 1 sizes. There's 1, 3, 7. Like, that's not a recurrence that you're used to seeing. And what I'm going to do is, this represents merging, whenever I have to merge 2 files together to go to the next size up, what I'm going to do is, I'm either going to add a file of size 1, or when I go to do this, I'm going to merge 2 files of whatever my smallest size is, while I insert the other element into the mix. So I'm going to do a merge and insert fused together. Otherwise, I'm only ever creating a file of size 1. So I have two ways that inserting works. It either creates a file of size 1 because there is at most one other file of size 1, or I'm doing a merge. I'm taking the two smallest files must have the same size, at which point in time I'm taking those 2 things, interleaving them using like the merge of a merge sort, but I'm also inserting one element as I do. Okay? It's kind of a funny way to build a data structure, I freely admit. But it's the one I came up with that I like. Now, this is not enough to de-amortize the algorithm. It is, however, enough to make it work very, very well for stream diffusion. Because I only ever have to do one merge. And so my merge structure, my merge tree has a fixed shape. Like, so I can actually compute it as a stream calculation using data.vector. And GHC is smart enough to unbox that thing all the way down and make it really fast. It actually can write faster code than I can. I can't figure out how to beat the code that Roman can generate for data.vector by hand. I haven't been able to write the code that he generates somehow. And I've tried because, in theory, there's a better point in the design space by using a different number system than skew binary. If I used skew quaternary, that on paper should be faster. Unfortunately, I'm not smart enough to write the fusion algorithm to make it go that will actually fit into GHC and fit into all the registry responses. So the theory says that should be a faster algorithm, and I just can't make it happen. If somebody can figure out a way to make that go without making it 10 times slower, that would be another thing. Like, this is, by the way, a very much a work in progress kind of talk. So, so let's see. So incrementing by 1 never carries more than one place. Each number can be represented exactly one way. We don't really need the uniqueness of representation. It is kind of nice from a normal form perspective. Okay. But so far, we've only talked about inserting. In that naive version of the data structure that I described, searching it is actually slower than searching a B tree, or searching a lot of things. And the reason is because I have to search each one of those files independently. I have log n files. I'm searching log n files. Each file takes me up to log n time. And so there's a log squared n in there. You know, I get to divide by b and whatnot. But in general, we've blown up by an extra log factor. Okay. So I resolved this using the technique that was described in the original paper called fractional cascading. And I obtained a data structure that inserted about 10 times slower than a map and searched about 3 times slower. Like I said, data.map has excellent constant factors. So that was the first step of this. Now, to understand what I did, we need to understand what fractional cascading is. And fractional cascading is a trick for searching a bunch of sorted arrays at the same time. Okay, that's exactly the problem that we have. We need to search a bunch of sorted arrays at the same time and tell you the answer of, it was in this array and this is the answer. And in general, we want to search m arrays that are each of the size up to n. Pre-calculations are allowed, but I really don't want you to blow up my space because, you know, space usage, time usage, and external memory are basically the same. This structure, this algorithm, fractional cascading, you can actually Google it. It's a trick by a guy, Leonidas Guibas. He originally he came up with it for working on computational geometry. It pops up all over the place in computational geometry. That's where I first saw it. It's also used in the Bender paper here. You know, naively, if we just binary search each of them, we're gonna have to search m arrays each in log time. And with fractional cascading, we want to pay that. We want to say, I want to search in log m n time together, you know, the composite size, and then that's log of m plus log of m. And how it works is cute. I guess you probably can't see the colors too well. So what we want to do is, let's just say we had 2 sorted lists. Let's just look at 2 layers of our cola at the same time. So we have 2 lists that happen to be in ascending order. I'm going to ignore values for right now, just because they don't add any. You know, let's just pretend my key and value are the same. As the cacheability is, you know, data set. And what we want to do is we want to just take like every kth entry from the second list. Like pick a constant k. I don't care what it is. Well, it's got to be bigger. And not too big. But here I'm using like every 3rd entry just because it fit on the slide. Okay, so take every 3rd entry out of this array and copy it up into this array and sort it into place. And so what I wind up with is a slightly bigger first array, such that I have these little forwarding pointers into the next array for each one of the things that I copied up. Okay, and what I want is when I'm done doing a search on the first array, I should know a constant size window in the next array to search. It's a constant size window because I took every kth element. So the window is of size k. Okay, this is actually kind of the thing that drives the Toku Tech fraction, at least the original paper on the Toku DB stuff. They don't do it that way though. They do it a different way. But the general idea, I think, is pretty straightforward. And so after a failed search in the first array, I only have to search a constant amount of space in the second array. So if I repeat this log n times, what I wind up with is a 1 log time search, and then log n 01 time searches. It's a funny way to get a log n, because I'm doing log n plus 01 times log n. To get log n plus log n is O log n, but I get a log time search out of it.
So that's where you get the bed constant?
This is the thing that I got the bed constant for, right? The thing that was 10 times slower than I wanted.
Yeah.
Because unfortunately, this required me to kind of scan the next file up in size to pull the data down, or I have to take this data out when I'm building this array. I have to build the secondary array of already pre-thinned data to avoid thrashing through the larger size. So I wind up with much worse cache hits than I would expect, or than I want. So this guy actually winds up accessing about 10 times as much memory as data when I go to implement this one. If you just turn on the set plus whatever it is that will tell you the shaka folder is. whatever tells me the space utilization or whatever of a GHI command.
Oh, so Shahar tells the space information.
Huh?
Shahar tells the space information.
Yes. So, anyways, that's what fractional cascading is. So now let me add something new to the world. So this is a better way to store this. When we went back to this thing, we had to store these forwarding pointers. Plus, I also had to store like copies of them very, very regularly because I could have a massive gap here. So I have to like store it like every like fourth pointer is just a copy of the last forwarding pointer or something stupid like that I can find it in the constant size window. This is awful. Okay. So what I want to do is I want to use the fact that we're copying regularly, like clockwork, every kth element of the next array. So if I could tell you how many forwarding pointers there are up to a given position in my array, if I could tell you like, oh, that's not a forwarding pointer, this one is, that one's not, that one is, and there's 500 of them up to this point, right? Then what I could do is I could just say multiply 500 times k, that's the position in the next array to start. Right? And so I could implicitly store the forwarding pointers. So this guy has to do with another neat, very underutilized corner of modern computer science. And that is this notion of a succinct dictionary. Okay? And so let's just say that we have some bit vector. And that's all I'm going to concern myself with today. If you want to see this like made insane, go look up wavelet trees. They're amazing and cool and have absolutely nothing to do with wavelets. Yes? Wavelet trees.
Wavelet trees.
Yes, they have nothing to do with wavelets. They're named by analogy.
Okay.
They're also the coolest data structure that I know of right now that isn't being used. They're I cannot recommend them highly enough as something to go through and obsess about for a couple of years. And they're really easy to implement. So all sorts of good things. You can amaze your friends. Anyway, so let's say we have a bit vector and it has like length n and it contains like k1 bits. Okay? Then there's n choose k such vectors. That's that basic combinatorics, nothing earth-shaking, right? And so without any deep insight into the universe, I could just tell you which one it was by giving you which number it was out of the n choose k possibilities. And we can represent that in log of n choose k, plus an extra bit bits. Okay, so that's. I'm not using anything about, well, I saw a 1, so I'm guessing that the next one will probably be a 1. I'm not using any context. I'm using 0 bits worth of context. I'm just saying, there's k of them that are set to 1, and there's n total. This is the permutation, the selection that you have. So it turns out that in the amount of space that it took to store this was the minimum amount of space that it took to store that bit vector at all, right? This is actually much smaller than the bit vector itself, often, unless you're exactly even, and even then it's smaller than the bit vector, because you know that it's even. If you have to store k as well, then you're going to get back to the size of the bit vector. But so what we want to do is, I want to say, in a little bit extra space, in an additive little o term, not a full constant multiple of h0, it's possible to implement a version of this algorithm that runs in O1 time. So we can make this very tiny index that is, this thing is already at entropy, basically, in terms of storage space. We're adding just a little bit more than entropy, not a constant multiple of an entropy to storage space. And we're saying that I can count the number of 1s or 0s up to a given position in my bit vector. Okay? And there are several such algorithms. Mihai Petroscu has probably the most interesting one. There's this thing called RM, there's one called RRR, there's a couple of things that are not technically succinct that implement this, that have very good constant factors, called rank 9 and POPI. Those are the things I use in practice. So the fact that this can be done in succinct space really just gives you the name for the class of algorithms. We don't tend to do it in succinct space. My data analytics project is all about doing it in succinct space, but that's Doesn't know better. Second. So the nice thing about this is I can tell you, if you told me, give me the rank of ones in my string up to position 7, I will tell you just how many ones there are up to position 7 in O1 time. And it's not a whole lot of space, right?
Is it really all one, or does it depend on each zero?
Absolutely O1. Let me show you, I'll explain a version of the algorithm that just runs in O1 time but takes 2 times H0 space. How about that? I can do that one. I can do that one off the top of my head. And that's just take this thing and say, well, this is a bit vector of length n. Break it up into chunks, each of size log n. Right? And then for each chunk, what I want you to do is I want you to store in a second vector. For each chunk, store the prefix sum up to that chunk. Right? And then to calculate the answer, what you should do is div mod by log n. That'll tell you which chunk you want to sum up to. Take the prefix sum up to the chunk and then pop count within the chunk. On a word machine, we can assume pop count is O1. So there's no one.
So that's how you get one.
Okay. That is an algorithm that does this in non-succinct space. To do this in succinct space, you have to use 4 Russian strings, and they're not something that I wanted to explain quickly. I'm happy to do that one. Anyways, so rank is one of 2 algorithms that we can do. Another one is called select, which will tell you the position of the ith alpha. And that can also be done in O1 in succinct space. That one's trickier. In practice, we often just do that one in logtime because the logtime algorithms have much better constants. And I don't need it for right now, so we're just going to focus on rank. But there is some very beautiful connections between them. There's a Galois connection between the two, so you can talk about the adjunction between rank and select, and you can play with the section and track situation. Go that's categorically. Nobody cares. Anyways, so we can do implicit forwarding by storing a for our vector. What we'll store is our vector of keys. Then we'll store a bit vector with 1 bit per key, saying whether or not this key is actually a forwarding pointer. And then we'll store a vector of values, but we're only going to store values for things that are not forwarding pointers. So in order to index into the key value pair, what we should do is we should look at the bit vector and say, well, is it true or false at this point? If it's true, then it's a forwarding pointer, and so we should actually go look at the next file. And what we should do to figure out where we're going to start in the next file is take rank in that bit vector up to that point, and that will tell me the offset in the next one. Multiply it by k. And if I wanted to actually look up the value, then I can go through and say, well, what was rank up to that point? And I look up that position in my value vector. Nicely, this is on video, so if that wasn't entirely clear, you can replay it until it doesn't. I don't know, but anyways, that's the idea. So we can use this rank structure to make it so that I don't actually have to store the forwarding pointers. I store them implicitly. And it takes an extra 1 bit plus little o of 1 bit per entry. So not quite 2 bits per record to store this extra structure. Okay, I can live with an extra 1.x bits per record. If we want to do deletions into our structure, because I haven't described anything about how to do deletions, you can send a record in that is a deletion by sending a similar bit vector along with it. And so for an extra couple of bits per record, you can do this. Now in practice, we don't use the succinct algorithm, so it's 2 bits. And then there's algorithms called rank9 and Poppy. Poppy is actually the conference for it hasn't actually passed yet, but it's actually a very good algorithm. Anyways, so implicit fractional cascading is still slower. So this is about 8 times slower for inserts. Inserts is about 3 times slower than data. So after all of that, I went through the pain, so I made you guys do it. It didn't help. Even with like novel contributions to the algorithm space, I only sped up my inserts a little bit and didn't really help my search time. So let's do a completely different approach. Let's go to what do people like to play with in big data? They like to throw around Bloom filters and hyperlog and things. So let's use a hierarchical Bloom filter. We'll use a hierarchical Bloom filter to try and cut our costs. How many people here are familiar with Bloom filters? Oh, good. So I don't have to really explain. How many people are familiar with hierarchical Bloom filters? All right, so I have 2 people. So the idea of a hierarchical Bloom filter is just taking a Bloom filter, and instead of like, if you had like 19 hash functions or 20 hash functions for your Bloom filter, you're going to be poking to 20 bytes anywhere inside of that entire array. Right? Say you have a 2 gig array. You're going to be writing to 20 locations somewhere within 2 gigs. That's god awful from a cache perspective. Right? We're going to be thrashing pages because we're going to be loading things from the page cache at that scale. So Christian Mitchemacher came up with this trick, and it's really just a trick, which is to say, what we can do is we can distinguish one of our hash functions and use it to pick a page. Now, I'm not being cache oblivious here. I've got pages. I've leaked page size information into my system. But what I'm going to do is I'm going to pick a page with one hash function, and then within that page, I'm going to use all my other hashes. Okay? And so now, I don't thrash 20 pages, I thrash 1 page, and I beat the ever-loving crap out of it 19 times. Okay? Now this takes knowledge of the cache size that I want to work with, my page cache or whatever it is. And it costs me about 2% of my Bloom filter space utilization. Okay, so I'm willing to take a factor of 20 speed up for 2% space loss. That's sort of the motivation behind using this kind of Bloom filter. I also have to give up its cache obliviousness. Meh. All right, so I'm no longer even trying to, my overall algorithm, if it uses this as a building block, is no longer cache oblivious, but it's cache oblivious-ish. I'm willing to hack. I'm willing to make this thing. I want it to run. I want to use it. I don't, the theoretical properties of it are not what drew me to this. I mean, the fact that I don't have to tune it very much, I mean, it would be nice if I didn't have to tune this too. But I don't have a cache oblivious form of a hierarchical Bloom filter. I keep playing with it, but I haven't come up with it. So now, if we play with it, I finally win! Inserts are finally faster. Considerably faster, actually. At about 10,000 inserts, we started about 5 times faster than data.map. And once we hit about 1 million inserts into the map, we actually are starting to hit about 12 times faster. On the other hand, lookups are awful. Lookups are like, 12 times slower across the board. So data.map is tooling us, or tooling me, I guess, when it comes to looking things up inside the map. So if you have a map that you're just going to write a whole bunch of stuff into and occasionally look at them, this might be a way to go.
Can you explain again how exactly you use Bloom filters here?
So what I'm doing is I'm associating with each file. I actually completely skipped this slide. Sorry about that. For each one of the arrays that I have, I'm associating one Bloom filter per array for like every array that's bigger than a certain threshold, right? And I'm saying this Bloom filter has its false positive rate tuned to the cost of having to do the binary search. Okay, and so as I go deeper in my Bloom filter, in my array set, I'm dividing by larger and larger number. My false positive rate has to get more and more anal retentive. It has to get much more precise about whether or not something is in the result. Because failing the Bloom filter cost doesn't get much bigger because it's like I had to load a page because it's hierarchical. But failing the search means I have to binary search a much bigger and bigger space, right? I'm talking about millions or billions of entries now. And so, it's still log of that. It's not ridiculous. But I'm basically some false positive rate divided by n, where n is the level. Where I'm 2 to the n plus 1 minus 1.
So do Bloom filters help you merge faster, or do
They help me search faster. In theory.
But you spin out inserts.
Yes. Because the inserts, before, I had to go through and play with the fractional cascading. I had to go through and, in order to do an insert, in order to make a file, I had to also go down to the file below it and copy up every so many entries out of it. Now I'm not doing that. I don't look at my ancestors, but the bigger things in the array below, the arrays below me, in order to build up the Bloom filter. The Bloom filter is a purely local operation. That's actually really nice because if I have several, I can compute them in parallel, I can do all sorts of things as I'm building this. I can even build them lazily, and that's what I do. So when I'm inserting here, I'm cheating by not building the Bloom filter until you go to look at that array. If you go to search something and it has to happen, then I have to build the Bloom filter. But in the meantime, it's just, here's a lazy thump that is going to eventually evaluate into this Bloom filter. And so if I'm just firing inserts at it, I don't pay for the Bloom filter until I start searching.
Okay, so you basically split up fractional cascading by removing fractional cascading.
Yes.
And paying the cost instead of lookup time.
Yes, and once you do the first lookup, you start paying for it. You then pay for it. Certain workloads, this may not benefit. As a matter of fact, lookups still are pretty awful. Like I said, it was like a factor of 15 slower. But you noticed before, lookups were actually not that bad. I think we were probably like a factor of 3 or something slower. I can't remember what it was.
3 and 8. There were 3 being fractional cascading.
Implicit forwarding, 8 times slower inserts, 3 times slower data searches. So searches suffered really badly when we switched to Bloom filters. So let's just not do them. Remember how I was saying I'm willing to give up a lot? Here I'm just going to give up the asymptotics that I was searching for, that extra log factor, right? If I just don't do the Bloom filter, how do we do? Well, my lookup slowdown is actually way better than doing the Bloom filter. What happened was I was sitting there tuning the Bloom filter parameters, and I kept cranking up the threshold at which I started Bloom filtering. And I couldn't come up with a workload that would fit in memory for which the Bloom filter was ever a win. So embarrassingly, by the end, I'm left with a very simple data structure that's relatively competitive. Inserts are really fast compared to data.map. Lookups get kind of slow at around 1 million records. And I'm starting to look up, 10,000 or something like that. And we're getting down to like 3.5 times slower. But being able to insert 12 times faster covers for an awful lot of sins. It's purely a functional, but the amortization of this assumes ephemeral access. You should only use the latest version of the map you've built. Yep, I'm just giving up on that. And in exchange, and we're just doing skew binary merges, and we let Fusion do this, and it's a 2 cola instead of a 4 cola. This is a study in compromises. This is everything I hate. But it actually performs pretty darn well. And it's easily portable. You can actually take the code here. The code here, more or less fits on a screen. I'll actually show it in a second. And you can pick it up and drop it into .NET or into Java or into any of those other ecosystems and just run with it.
So not like finger trees.
Huh?
Not like finger trees.
Yeah, finger trees are god-awful to port.
I tried 3 times, I think.
Yeah, this is actually something you can just pick up and drop in and get a reasonably efficient map that is write mostly and can do range accesses. Okay, and so that was kind of an interesting result. Colas are designed for this big external memory use case, and this is me saying, well, if I'm doing it in memory, perhaps the right answer is to get rid of a lot of the stuff that just makes it the constant factor stuff. And accept the fact that I'm working with a log squared time lookup structure that just happens to have constant factors that are good enough that I don't care. We're willing to give up an extra log factor here and there to do linear scans instead of binary searches and all these other things that people do. So perhaps this is one of those cases. And this is not the most compelling story that I wanted to get out. I didn't want this to be the answer. I didn't want this to be the thing that I walked away from this project saying this is the right thing, this is what I'm getting. Because when I look at it from the standpoint of when am I going to hate myself in 2 years for having wasted time on it when the right thing becomes the right, the fast thing. I don't know. So I can pull up the actual code for this. This is actually off of a simplified branch. It's a little bit lobotomized. In the actual code that I use, I specialized the files of size 1 because it rather dramatically reduces the memory footprint and speeds up the whole thing about 25%. But the complexity isn't worth it for Expedition. So a map, just for reference, I have this array type here, which basically gives you an unboxed as possible vector that isn't necessarily unboxed. So if you're storing things that have pointers in them, it doesn't get unboxed. But if you're storing ints and whatever, it unboxes. Okay. And so I build the whole map off of that, and that way I get to store unboxed ints in my nice beautiful data structure rather than boxed things that throw away all the benefits that I got from coherence. So we go look through the code here. We have a map is either empty. I should probably zoom this in a bit. So map is either empty, or we know its size. This is, I think, the size of the chunk, actually. We have an array of keys and values of that size. I'm not doing deletions in this version here. And then I have a tail. That's the rest of the map. And so each of the chunks inside of here is going to be bigger. And they're going to be on a skew binary progression. So 1, 3, 7, 50, etc. There are going to be some power up 3 to the k plus 1 as well. And we can answer whether it's null by answering if it's null. We can make the empty map. We can make a singleton map. These are not terribly earth-shaking operations. We can look up by binary search. If it fails, keep going. Lame. But it works. We check to see if something is within threshold by seeing if it's within a factor of 2 of the next guy up, which is actually enough to be just slower than the 3 is less than 7. So, anyway, works out. So an insert is one of 2 cases. It's either you have 2 maps or 2 things that are of the same size. This really would normally be in the algorithm that I've described so far, assuming that the skew binary is really canonical, we would just be checking that n1 is equal to 2. When we start allowing for splits and things like that, you actually wind up with some things that subtly violate the invariant. So I actually want that threshold to work one way. If you start allowing for deletes, it happens a little bit more. And so what we're going to do is we're going to use Stream Fusion to go through and zip these 2 guys together. Zip these 2 guys together, merge those streams together, spit out a pair of vectors as a vector, and build up my map. So I'm just using Stream Fusion to do all the work. So I have a couple of Stream Fusion combinators that I've implemented in another module. But they do the obvious thing. I'm going to insert this key value pair at the right place inside the stream, and I can zip 2 streams together. And I can merge. So those are the 3 operations that I'm going to be using from Stream Fusion, or from my custom Stream Fusion. And if I didn't have 2 arrays that were the same size, make a singleton and bolt it onto the front of this thing. Because I didn't have 2 1s, because otherwise this case would have happened. So I didn't have 2 things of the same size, so it's perfectly okay for me to put a smaller thing in. So that preserves my invariance. That's insert, that's lookup.
Does it make sense to specialize this for the small sizes?
It does make sense to do it, at least for the singleton case, and that was worth about 20% to do it. And it actually rather dramatically cuts the memory footprint because having a 1 constructor on my data type, that's a heck of a lot smaller than these things. The arrays are pretty hefty because they have starting offsets and all this kind of stuff. So those things wind up being 70 bytes a piece or something like that, whereas the other guy is 1 structure that's a quarter of the 5th of the size, or something like that, plus a loss of an interaction. There's all sorts of benefits. So that's singleton, lookup, threshold, insert. Converting from list is literally just doing the inserts one at a time. I actually built up something that very carefully checked to see if I was doing things in monotonically increasing order, and then restored all my invariants and smashed things together. So. Search is maybe the only thing here that is interesting is that I use an offset binary search. Paul Kwong did a article at one point in time showing how you generally don't want to do pure binary search because from a cache perspective, it's actually pretty awful because the caches that we have for L1, L2, et cetera, are like k-way set associative. And so when you're hitting exactly on powers of 2, you're thrashing the same cache slots as you walk down, no matter which way you go. And so you want to just offset it a little bit, and that actually turns out to make an embarrassingly decent dent in the performance of this at scale. And it's not an appreciable difference to the usual binary search. So if you want another just like stupid 20 character takeaway from the talk, do offset binary search, it's easy. And that's the code. That's the code for a slightly simplified version of it that doesn't have splits and a couple of other things. But that is actual. So, in summary, if you don't like the problem, change the problem. I gave up on worst case asymptotics. I gave up on persistent amortization. I gave up on the asymptotic bounds completely, and the thing still fixed.
How much faster is it for range queries?
So range queries, it's basically indistinguishable from the B-tree. The asymptotics of it are right. And so, I mean, in general, you're gonna pay to scan through log n things, so you can hold all log n things in the cache.
Oh, so that lookup is for single lookups.
Yeah, those are the slow lookups that I said I didn't
Who
care
cares about those?
Yes. I didn't actually show the fact that the range lookups are actually good. Because I don't have benchmarks for it. If somebody wants to throw benchmarks at it, yeah. So.
Why did you specialize only for the one element arrays? Seems like
Because I tried 3s and 7s and I couldn't get them to pay. They didn't pay out. It turns out mostly because of quirks of the stream fusion stuff. And this is why I was starting to say that stream fusion has been both a benefit and a curse. It is a benefit because it makes the binary case way faster than it has any right to be, because I can't write it that fast. It's a curse because I can't do the quaternary case that should be the fast one. And I haven't been able to make it scale to do the 1 and 3 element special constructors. I got the one element constructor to work, but it was a very narrow thing. So I actually think that I'm giving up most of the benefit that I have in the fusion there, and I'm only winning because of the extra space. So if I can figure out a way to write the fusion better by hand, then perhaps I can make a bigger dent by adding in constructors for 1 and 3.
So is it faster even for 3 than like a handwritten?
A handwritten 1 is fast. Adding a handwritten note for 1s is faster right now. I'm not currently getting a win out of trying putting it in for a 3. When I put in 3, I actually slow down by a factor 10. It's really brittle in that regard, and that actually doesn't make me happy. Because at that point in time, it seems that what happens is, I mean, literally compilation slows down to like 4 minutes. Because we're asking like spec conster and all this kind of stuff that's designed to optimize inside a data.vector to do things like just handle a bazillion cases, and it just can't. It can't fit that into like the instruction cache usably. So that seems to be the problem that I've had there.
Would it make sense to like have a number system that can have something much more than 2 in the least significant position based on the unboxed array size out to something?
Well, that's what I was using. That's what I was using the skew quaternary for. So you can wind up with a 5. And in practice, that on paper should look right. That's the.
So it has zeros and ones in the tails and has up to 4.
Oh, just starting the number system, like using variable radix. That seems viable. I haven't actually tried it though. If you wanted to throw patches at it, I would do it. And it actually should be quite doable. if you actually look at the code with the ones case expanded, there's a branch that has the 4 cola in it, there's another branch that has the 3 cola. Both of those, the code for it is actually very simple. I had something else there I wanted to. So there's a few things that we can do that's a little bit different than this. So the first thing I said was that how am I doing on time?
We were past our time, but
Okay,
Keep going.
I'll try to.
Yeah.
No rush.
So the thing that is interesting to me is that one of the things I mentioned back here was that the version of this that used implicit fractional cascading was an improvement on an algorithm for this thing called a stratified doubling array. And one of the things that they do for the stratified doubling array is they build they actually build like a MVCC kind of database that works off of this stuff. And what they do is they replace the one file at every level with kind of a set of files and a set of versions, and they make this very complicated set of reasoning for it. Subject to the condition that like every version that is within a given file has to have at least a third of the records or something in that line. I could build a version of this that did that MVCC framework. Did I hit a button or something?
I have no clue what that is.
All right. Anyways, I could implement that MVCC framework, and that would let you do things like split and stuff like that that are impossible with the current API. I turned all the volumes down. I got it. Anyways. All right. Anyways. But the API wouldn't be very Haskell. And so there's a middle ground somewhere between the full persistence and the ephemeral state that I've got right now that I haven't figured out. Maybe there's a very lensy API that you put the actual current overall map inside a state somewhere and then track versions as the objects that you're manipulating. The API would feel very different though. And so I kind of shied away from doing that. But that would let me do more operations. And that's like the major kind of outstanding bit of theoretical playing around that I've got. So that's, again, gave up on everything that I wanted, but it's still fast. And so I think I'm well out of time. So there's a bunch of things I didn't get a chance to talk about, integrating deletes and range queries. The original motivation for this was to use it as a backend for my sparse matrix multiplier, because that yields a notion of like a planless table join when you actually get, like, there's some really neat stuff that comes out of that. That lets me go through, and when I can combine it with the compressed Morton stuff that I have from analytics, you get all sorts of neat database kind of tool buttons. We can borrow the MVCC approach, I just mentioned that. And I really cannot stress strongly enough how important I think wavelet trees are. They're probably the coolest data structure that I've seen. Yes. And there's an interesting wavelet trees for everybody or something like that. Wavelet trees for all paper by Navarro. His description of wavelet trees at the beginning of it is awful, but the rest of the paper is amazing. And so if you have to read another paper to understand what a wavelet tree is and then read that paper to find all the utilizations of it that people have, it's interesting because it's a data structure that's really only become viable in the last couple of years, like last few years. It's new, and that's not something you see all the time. And then Stream Fusion is just a blessing and a curse. And there's some neat stuff that you can do using the wavelet tree stuff by repurposing some of its underlying technology. We talked about how to do unbox vectors of some types and be able to say, here's a way to unbox anything. And that will probably be another topic. questions?
Am I understanding correctly that Bloom filters wouldn't help you anyway for range queries?
Not at all. I use to do the range query, I wind up just finding the start of the range, end of the range, and I just scan through all of them, merging as I go. So it's a K-way merge, and because K-way merges tend to be good for caches.
All right, thank you.